So, good morning, sir. So, I am Nico Kagabi Quinto, and I will be the one who will discuss big O notation. So, let's start. Big O notation. What is it? And big O notation is a simplified of an algorithm's efficiency. So, it gives an algorithm complexity in terms of input size n. So, it is machine independent. So, it is not dependent on machines, and Big O examines basic computer steps and also analyzes time and space. So types of measurement of big O notation. So worst case, best case, average case. So when we're talking about big O, so kadalasan ang ginagamit is worst case. So it doesn't mean na hindi na importante yung dalawa, yung best case and average case. And general rules. So general rules of big O. So, number one is ignore constant. So 5n. So, ang 5n is sa big O, ang kakalabasan is O of n, which is in-ignore na yung constants, which is 5. So, number 2, certain terms dominate others. So, ito yung list. So, O of 1, O log n, O of n, O n log n, O of n squared, O of 2 raised to n, and O of n. I don't know how to read that. And ignore low order terms. So, big O complexity chart. So, ito yung example ng big O complexity chart. Constant time. So, ito yung example ng constant time and how to get the big O. So, ito yung problem. X is equals to 5 plus 15 times 20. So, independent of input size n. So, kino-consider siya na O of 1. So, ito yung answer, big O of 1, which is ini-ignore niya yung constants. So, dito naman tayo kung sequence ng statement. So, the problem is x is equals to 5 plus 15 times 20, y is equals to 15 minus 2, mean x plus 1. So, how to get the big O? Paano natin makuha? O of 1, ito statement na to. And O of 1, lahat sila of 1 because ini-ignore natin yung constants dahil to sa general rules. So, O of 1 plus O of 1 plus O of 1. So, para 3 times O of 1 in short. So, ang sagot is O of 1 kasi nag-base pa rin tayo sa general rules, which is in-ignore yung constant.
Hi guys, my name is John Daniel V. Salvador, and based on naman tutorial, explain ko yung linear time complexity. So, if you write an algorithm whose execution is dependent on the input size, then it is said to have a linear time complexity. So, sinasabi lang naman dito sa description na to is ang linear time complexity ay dependent sa input size. So, kagaya ng code na to, for example, ito ay isang for loop. So, itong print x, it will execute sa number of times kung gaano kadami yung for loop na to. So, ang time complexity natin is big O of n. Kasi nga yung n times itong print x is yung big O of 1. So, n times big O of 1 is equals to big O of n. So, alam natin na kapag itong n times big O of 1 is equals to big O of n. So, next example. Dito, sa example na to, it will drop the low order items kasi nga, itong big O of 1 is constant na yan. Alam natin, constant na yan. So, ito namang for loop na code na to is big O of n. Kapag kinuha natin yung total time, pinagsama natin, big O of 1 plus big O of n is equals to big O of n. So, kukunin natin yung worst case scenario. Worst case scenario niya is big O of n. Next, quadratic time. So if time execution of an algorithm is directly proportional to the squared size of the input size, and then it is said to have a quadratic time complexity. Uh, ang sinasabi lang naman sa description nito is uh, nakadepende rin siya sa input size ng ano natin, kagaya nung sa linear time. Pero dito kasi, directly proportional to the squared size. So, kagaya nito, example, nested for loop. So, ipiprint niya tong x times y with the number of times with, tapos itong for loop na to, i-execute niya din with the number of times. So, doble. So makita natin na mag-execute lang yung print statement ng n times n kasi nasa nested for loop tayo. Kaya ang time complexity natin ay big O of n squared. Next. So dito din ang time complexity sa block code naman na to is ang time complexity din natin ay big O of n squared. Dahil alam natin ang complexity ng bawat code ay big O of 1. So ito alam natin ang values na is constant, kaya big O of 1 yan. Dito naman, for loop example, hindi siya nested, so big O of n. Kasi it will print x the number of times, with the number of times. Ito naman, sa baba is nested for loop. So it will print x times y with the number of times. At i-execute nyo yung for loop na yun with the number of time din. So pag pinagsama-sama natin yan, kasi ang max nila is, ang total time nila is big O of 1 plus big O of n plus big O of n squared. So, kukunin natin yung worst case scenario ay kaya ang time complexity ng code block na to is big O of n squared. So dito rin, for same as this example na na-explain na ni Nico na palagi natin na kinukuha yung largest runtime at worst case scenario. So, pag alam na natin yung code, time complexity ng bawat code. So, if example, ito, ang time complexity niya is big O of 1. Ito naman, big O of log n. At ito naman, big O of n squared. So, pag kinuha natin yung total time nila, pinagsama-sama natin sila, syempre, alam natin na kinukuha natin yung worst case scenario, ang time complexity ng code block na to is big O of n squared. So, yun lang.
Little o notation is used to denote an upper bound that is not asymptotically tight, a theoretical measure of the execution of an algorithm, usually the time of memory needed, given a problem size n, which is usually the number of items, informally saying some equation f of n is equal to little o of g of n. Means, f of n becomes insignificant relative to g of n as n approaches infinity. Note that in this definition, the set of functions f of n are strictly smaller than c of g of n, meaning that little o notation is a stronger upper bound than big O notation. In other words, the little o notation does not allow the function f of n to have the same growth rate as. Let f of n and g of n are the function that map positive real numbers, we can say that the function f of n is little o of g of n. If for any real positive constant c, there exists an integer constant n sub 0 less than or equal to 1 such that f of n greater than 0. Mathematical relation of little o notation. Using mathematical relation, we can say that f of n is equal to little o of g of n. Means that as the n approaches infinity, f of n becomes insignificant compared to g of n. In addition, the inequality in the definition of little o should hold for any constant, whereas for big O, it is enough to find some that satisfies the inequality. If we drew an analogy between asymptotic comparison of f of n and g of n and the comparison of real numbers a and b, we would have f of n is equal to big O of g of n, almost equal to a less than or equal to b, while f of n is equal to little o of g of n, almost equal to a less than b. Example on little o asymptotic notation. If f of n is equal to n squared and g of n is equal to n cubed, then check whether f of n is equal to little o of g of n or not. The result is 0 and it satisfies the equation, so we can say that f of n is equal to little o of g of n.
Good day, everyone. My name is Jeffrey Avasapla from BSCS 3A This report is about the time and complexity or time complexity of algorithms for the omega notation. Omega notation represents the lower bound of the running time of an algorithm. Thus, it provides the best complexity of an algorithm. So, omega gives the lower bound of a function. This figure described, or it can be described as a function n, belongs to the set of omega g of n. If there exists positive constant, or c, such that it lies above cg of n for sufficiently large n. For any value of n, the minimum time required by the algorithm is given by the omega g of n. So, we're to use a big omega notation. So, big omega notation is the least used notation for the analysis of algorithms because it can make a correct but imprecise statement over the performance of an algorithm. Suppose a person takes 100 minutes to complete a task. Using omega notation, it can be stated that the person takes more than 10 minutes to do the task. This statement is correct but not precise, as it doesn't mention the upper bound of the time taken. Similarly, using omega notation, we can say that the worst case running time for the binary search is omega of 1, which is true because we know that the binary search would take at least would take at least constant time to execute. Again, this is Jeffrey Avasapla from BSCS 3ABA reporting the time complexity of algorithm for the omega notation. Thank you.
Theta notation. Theta notation encloses the function from above and below. Since it represents the upper and lower bound of the running time of an algorithm, it is used for analyzing the average case complexity of an algorithm. When we use big theta notation, we're saying that we have an asymptotically tight bound on the running time. Asymptotically because it matters for only large values of n. Tight bound because we've nailed the running time to within a constant factor above and below. Theta bounds the function within constant factors. A simple way to get the theta notation of an expression is to drop low order terms and ignore leading constants. Dropping lower order term is always fine because there will always be a number n after which theta of n3 has higher values than theta of n2 irrespective of the constants involved. The expression can be described as a function f of n belongs to the set of theta of g of n if there exist positive constants c sub 1 and c sub 2 such that it can be sandwiched between c sub 1 of g of n and c sub 2 of g of n for sufficiently large n. The above definition means If f of n is theta of g of n, then the value of f of n is always between c sub 1 of g of n and c sub 2 of g of n for large values of n greater than or equal to n sub 0. The definition of theta always requires that f of n must be non-negative for values of n greater than n sub 0. If a function of f of n lies anywhere in between c sub 1 of g of n and c sub 2 of g of n for all n greater than or equal to n sub 0, then f of n is said to be asymptotically tight-bound.
So, hi sir, I am Franz RBB Tattao, BSCS 3A BA student. So, I'm here to discuss and analyze the running time of an algorithm. So, the running time of an algorithm for a specific inputs depends on the number of operations executed. The greater the number of operations, the longer running time of an algorithm. So, this is the graph. Ito yung graph sa functions, graph functions commonly used in the analysis of algorithms, showing the number of operations n versus input size n for each functions. So, runtime analysis is a theoretical classification that estimates and anticipates the increase in running time or runtime or execution time of an algorithm and its input size, usually denoted as n, increases. So, algorithm analysis is an important part of broader computational complexity theory, which provides theoretical estimates for the resources needed by any algorithm which solves a given computational problem. So, in computer science, the analysis of algorithms is the process of finding the computational complexity of time, storage, or other resources needed to execute them. So, yun po.
So, time complexity. So, what is time complexity? So, by the definition, the time complexity is the amount of time taken by algorithm to run as function of the length of the input. Here, the length of input indicates the number of operations to be performed by the algorithm. This gives a clear indication of what exactly time complexity tells us. It is going to examine the total of execution time of algorithm. Rather, it is going to give information about the variation, increase or decrease in execution time when the number of operation increase or decrease in all algorithm. So yes, as the definition says, the amount of time taken is a function of length of input only. So to elaborate, time complexity measures the time taken to execute each statement of code in algorithm. So if a statement is a set to execute repeatedly, then the number of times that state gets executed is equal to n multiplied by the time required to run that function each time. So for example, look at the code below. So the first algorithm is defined to print the statement only once. The time taken to execute is shown as 0 nanoseconds, while the second algorithm is defined to print the same statement, but this time it is set to run same statement is for loop 10 times. In the second algorithm, the time taken to execute both the line of code, so for loop and print statement, is 2 milliseconds, and the time taken increase as the n value increase since the statement is going to get executed n times.
Space complexity. The space complexity of an algorithm or a computer program is the amount of memory space required to solve an instance of the computational problem as a function of characteristics of the input. It is the memory required by an algorithm until it executes completely. Space complexity of an algorithm represents the amount of memory space needed by the algorithm in its life cycle to refers the total amount of memory space used by an algorithm, including the space of input values for execution, the space occupied by variables in an algorithm or program to determine space complexity. Time complexity is the time taken by the algorithm to execute each set of instructions. It is always better to select the most efficient algorithm when a simple problem can solve with different methods. Space complexity is usually referred to the amount of memory consumed by the algorithm. Although space might be critical, such as in embedded devices, there is not much value of space complexity in general. On the other hand, the time complexity is the critical factor of a cryptographic algorithm, especially in encryption and decryption. It should produce data fast enough. So, a variable part is a space required by variables whose size is totally dependent on the size of the problem. For example, resorption, stack space, and dynamic memory allocation. And if we want to compare standard sorting algorithms on the basis of space, the auxiliary space would be better criterion to than space complexity.
Good day, my name is Daniel H. Bertrantino from BSCS 3ABA. So for today, I will be discussing the time and space complexity example. And of course, gaya nga ng sinabi nila, that time complexity of an algorithm quantifies the amount of time taken by an algorithm to run as a function of the length of the input. Similarly, space complexity of an algorithm quantifies the amount of space of memory taken by an algorithm to run as a function of the length of the input. So basically, the time is ito yung kung gaano karami yung nako-consume na oras ng algorithm kapag iniran na siya or kung gaano kabilis yung algorithm kapag niran na siya. So, sa space naman, nagpa-pertain ito dun sa may availability and dun sa may specs ng devices natin. And of course, yung space is the phase or ito yung itsura ng data structure natin na gagamitin para dun sa may algorithm. So, of course, there's a few types of solutions that we can use to compute the time and space of an algorithm. But for today, I will be using the sorting algorithm. So, sorting algorithm is one of the usually types of solution na pwede natin gamitin para makita natin o malaman natin kung ano ba yung time and space complexity ng isang algorithm. So in sorting, we have of course the bubble sort, insertion sort, and selection sort. But ngayon ay gagamitin natin sa bubble sort because it is easy to understand and madali lang siya. So here is the examples of bubble sort. So let's say we have here a example array. So we have 5, 4, 2, 1, 3. So we are going to sort it out in increasing order. So, basically, yung rules sa ating sa pagsusort natin when it comes to bubble sort is titingnan lang naman natin yung first index natin or first element natin at i-compare lang natin siya dun sa may second element natin or sa second index natin. If the first element or the first index is greater than to the next element or to the second index, then definitely we can swap it. So, like this one. So, we have 5, 4, 2, 1, 3. So, basically, 5 is greater than 4 and may sort, masaswap natin siya. So, 5 is greater than 2. um, masaswap din natin ulit siya. Masaswap din natin ulit siya. So, titingnan din natin dito is 5, of course, is greater than 1, and masaswap din natin siya. And lastly, 5 is greater than 3, is masaswap din natin siya. So, basically, hindi pa natin siya na-sort out into increasing order, but the first element or first index natin ay tama na yung pwesto niya. So, basically, dito na yung stop nung first pass natin. So, basically, this would be the space. Diba? Makita natin yung space of our first pass. So, second, ay titingnan din natin is yung 4, which is our first element na dito sa may initial unsorted array natin, which is the 4, 2, 1, 3, 5. So, titingnan natin dito is yung 4. Of course, 4. So, ayan. 4 is greater than 2, and masaswap din natin siya. So, ganun lang mag-bubble sort. So, isa-sort lang natin siya. So, next naman is the first element again is, or first index natin is 2. So, 2 is greater than 1. So, mas-sort natin siya. So, ito na yung increasing order ng ating example array kanina. So, makita natin dito is na kung mabibilang natin dito kung ilang beses siyang nag-swap at kung ilang beses siyang magsaswap nga para yun na yung pinaka-ating time and complexity ng ating bubble sort na algorithm. And of course, that would be all. Thank you for watching.